Good morning, dear student. Let us take up the last topic in module 3, that is controllers. Let us understand what are controllers, basic structure of a controller, types of controllers, their advantages and disadvantages in this video. What's the definition of a controller or what is the job of a controller? Controller job is to keep the controlled variable constant or a desired value. Okay, a job of a controller is to keep a controlled variable as a constant value or a set point value. Whatever we desire, that value has to be maintained for that controlled variable. That's the job of a controller. Okay, so what is the advantage of having a controller? We keep up the set point constant, what we call controlled variable is maintained at the set point, and it also improves the accuracy of the system. Steady state accuracy will be increased. What is accuracy? Accuracy is the closeness to the true value. Since we are maintaining the set point here for the controlled variable, so we see that the accuracy will improve through reducing the steady state errors. Okay, how can we approach to the set point? Set point we can approach by reducing the steady state errors. So indirectly we are going to control the steady state error here. Okay, and also we controlling the overshoots. We are also trying to reduce the overshoots which can happen in the response of the system. Okay, so overshoots are controlled, and we say that steady state error will improve. That is, we are reducing steady state error and accuracy will be improved. We maintain the controlled variable value as the set point value or the desired value, whatever is fixed for that. The basic block diagram of a controller. Basic block diagram of a controller, looks like this. Here we have the figure which shows the different elements of the controller. Primary element what we have is error detector. Error detector is very important component here, because this is the one which is generating the error signal, and error signal in turn initiating the control action. Okay, and that control action is forwarded to the plant, that is system. Okay, so error detector is very important. In error detector, what we do, there we do comparison. Comparison is happening. That is, set point is compared with the actual output. If there is any error, that error signal will tell us whether the output is above the required level or below the required level, whether to push the signal or pull the signal. All these things, actions, will be initiated based on the error signal. So this is what we have, the basic what we call block in a controller. Along with that, we will be having amplifier sometimes, because error signals will be very weak. Electrical signal, if it is weak, will be having an amplifier. And we have in few cases we will find that transducers are required in the feedback path. That is, while feeding output back to the error detector, we see that the physical system will not be giving always electrical signal as an output signal. It will be some physical quantity. So we have to perform here signal conversion, or what we call it as a transducer. That is, energy, that is, any physical energy is converted to equivalent electrical energy. And here in the error detector, we will be doing the electrical signal comparison. Internally subtraction will be performed and error signal will be generated. So this is about the different blocks, essential blocks in a controller we come across. Based on the action initiated by the controller, we can classify the controller into these many different classes. Okay, the first one we have on-off controller. In an on-off controller, the controller job is just to switch from one level to the other level, just a switching action. Okay, just switching action it is doing. Proportional controller we have, that is output and the errors input and error signal and the output signal will go, in proportion. They will go in proportion. And in integral, we found that the error signal is integrated, appears as a control signal. In derivative controller, we found that the error signal is differentiated and taken as a control signal. And we have in the next case, proportional and integral together we have in combination, that is, in an additive mode, that is proportional effect is added with an integral effect, and finally the control effect is generated. It is the, addition which is happening. We are having these two in a parallel path, and we will see that signal is passed through both proportional and integral, and the response is added to compute the controller output. Then we have proportional and derivative controller, that is sixth one we have. Again here proportional and derivative combination, we go for it. And we have seventh one, that is all the three, combined, that is proportional, integral and derivative controller. All the three we will be taking it together. What is an on-off control? As we have seen in many control systems, we don't need any big decision to be taken. Only we need to turn on some devices or turn off some devices. So if I take an example of a thermostat in a temperature control unit, what's the job of it? It is to maintain a temperature constant. How it will maintain temperature constant? If a temperature is going above the set point, it may turn on a compressor. Okay, and if it is going below a set point, it may turn off the compressor. Similarly, if temperature is below a set point, it may turn on the heater, or if temperature is going above, it may turn off an heater. So it is hardly job here. Controller system job is to turn on, turn off. Only two job it will be doing. Okay, so a very simple controller it is. And if the frequency of switching is very high, then it will lead to lots of ripple in the system, and it leads to unnecessary oscillatory behavior, which is not accommodatable, and this is not encourageable, which definitely disturbs the stability of the system. It has to be avoided. So this is what the constraint we have. So high speed switching controller design, we have lots of problem. Otherwise it is a simple structure. Only on and off is what the job done by the controller. Very simple controller it is. Next we have a proportional controller. Okay, how a proportional controller look like? So as we have seen that there should be a error detector block we have here. It takes this set point, it takes the output, and it compares by performing subtraction, and error signal will be generated. This error signal is passed through a block, we call it as a proportional block. Okay, so it is having a gain of Kp. What is Kp? Kp is proportional block gain, or you can call it as a proportional sensitivity. Okay, it will get multiplied and it appears as an output M. Okay, so in time domain, I can say that M of t is equal to Kp into E of t. Take a Laplace transform, you will find it as M of s, and Kp is constant as it is, we will take it. E of t becomes E of s. So therefore, I can write an expression for Kp, which is equal to output M of s divided by the error signal E of s. Okay, so we define a proportional control action this way. In a controller with a proportional control action, there is a continuous relationship between the output of the controller M and the actuating error signal E. Okay, they will be in a continuous relationship. If one increases, the other will also increase. If the other decreases, the first one will also decrease. It has to decrease. So it is like that. It will be having one-to-one relationship. That is what the meaning of a proportional controller. What's the advantage? Rapid response reduces the rise time. Okay, so response speeds up here by adding a block Kp here. You will see that the response time improves, or rise time is reduced. Okay, that is the speed of the system increased, we can say. Okay, steady state error also reduced to some extent, but it will not be fully eliminated. Okay, disadvantage if we want to mention, steady state error is not eliminated, which we wanted to eliminate actually, but it is not eliminated. And it leads to instability due to the rise in the overshoot and oscillations. So if you are having a, what we call, you will see that the overshoots and oscillations, which is the cause for the instability, that we are not controlling in this proportional controller. So that's what we call it as a disadvantage of this controller. Okay, so next we have integral controller. So you will be having a, what we call it as a, you will be getting something like a triangular wave, response you will be getting, because integration is what happening, that is error signal is integrated here. Okay, in a controller with an integral control action, the output of the controller is changed at a rate which is proportional to the actuating error signal E of t. Okay, so here it is what we are having some integration performed here. So we have ki divided by s is what the block gain here. Okay, so it is it is also as a reset controller, we call it as. Okay, so above we have a transfer function of this, because we can write you can write a equation something like this: s into m of s is equal to ki into e of s. This is the Laplace transformation taken for the definition of this integral controller which we have here. Okay, integration of error signal is happening. Okay, integration of error signal is happening here. So this is what we think, this is what we got it here. Advantage: the rapid response reducing the rise time, as we have seen in the proportional controller. We have the same here. You will find that response is very fast, it reduces the rise time. But we have very interesting advantage that it eliminates the steady state error completely. It eliminates the steady state error offset completely. Okay, since we are integrating the signal here, we could see that output will completely reach the input point. Since it is reaching the input point, expected point, then the deviation will not be there. Since deviation will not be there, steady state error will be 0. Disadvantages: we found that this is less stable. Why? Because we have a pole at the origin. Whenever we have a pole at the origin, they are all the system which is very prone to the instability. A very small change in the instability causing parameter, a small change can lead to system becoming unstable here, and it also increases the settling time. So increases the settling time, though the response time, rise time is fast, but settling time is increased. This is one disadvantage we have. So, and also it is less stable. The major advantage we can say that it eliminates the steady state error. That is a wonderful advantage we can call it as. Derivative control. In a controller with a derivative control action, the output of the controller depends on the rate of change of error signal E of t. So whatever error signal, that will decided by the that will decide the output definitely. And this is what the derivative controller block what we have here, differentiation is happening. According to the definition of the derivative control action, the output is equal to what? You are differentiating the error signal and multiplying with a constant, block constant. What is that KD is called? It is a derivative control action constant. It is a derivative control action constant, you can call it as. That is what the M of t available. Take the Laplace transformation of that. You can get an expression for the transfer function, we can call it as, that is output M of s divided by the error signal E of s. Okay. Advantages: it reduces the settling time, it reduces the overshoots. Disadvantages: it is not possible to use alone. You will not find a controller which is doing only derivative action. derivative action alone you cannot design. It is always it is always attached with a proportional controlling action. You can have alone, you will not get it. That is a design constraint, we call it as. Steady state error is not eliminated completely, it is still existing, whereas in integral controller we found that it is eliminated completely. The system is very slow because every time it has to differentiate, multiply, and make it available. This differentiation computing difference takes always time, it is slow. Always it opposes the changes, so you will see that output build slow, and amplifies the noise at high frequencies. Okay, apposition will increase. Apposition offered by the controller block increases at the higher frequencies. So you will see that it amplifies the what we call noise at high frequencies. So, it also advantages, if we mention, it reduces the settling time. It compared to previous case, what we have seen in integral controller, we found that, settling time increased there we have seen, but here settling time decreases. Okay. And it also reduces the overshoots. So overshoot reduces, settling time improves in this case. Okay. And disadvantages alone we cannot use it, that is the derivative control action alone you cannot have it, and this is very slow and it amplifies noise at high frequencies. These are all the drawbacks of the derivative controller. Comparison of different types of controllers. So what we are doing here is we are trying to compare all the 4 controller which we have discussed so far. So, this is a response time and the response time and a overshoot and error, that is steady state error. These are all the 3 major parameters in a time domain specifications which we have learned. So we are going to compare these 3 performances now. First, you take on-off controller, then we found that the response time is very, very small. That means, it is instant. Switching is instant. It has to happen instant. So, it should be very, very fast. And we say that response is very fast. Our response time is smallest, we call it as. The system is very fast. Overshoot is highest. This is the drawback of on-off control system. So we found that due to ripple, we found that there are so many overshoot issues. It is highest, and obviously the steady state error is large. Proportional controller, we found that it is also fast. It is this is also fast, but not as fast as on-off controller. So the overshoot also there, but not as big as on-off control. Error is comparatively reduced. Error is reduced but not eliminated. In integral, what we found, response time decreases. Okay. So the speed, is coming down. We say that response time, and it increases, overshoot increases. That spikes, all those shoots up we have in the response. That will increase, but not as big as proportional controller, not as big as this on-off controller. But advantage is steady state error will be 0 in an integral controller. Derivative controller, we found that the response time increases, overshoot decreases. You can see in this column, overshoot column, you will see that only derivative controller which is decreasing the overshoots. So whenever overshoot is troubling us in any system design, that is if output response is not observable with these overshoot, which is introducing lots of error in the system, then derivative control is the only option we have to snub these overshoots. You don't have any other system which can decrease the overshoot like a derivative controller. Next is error, and that will be there. It will not be eradicated, but it will be very, very small. So always we found that we will be using these controller in combination. Okay, so first combination what we can have is proportional and integral together. So we are going to have it in combination, so that advantages of proportional controller as well as advantage of integral controller, we can have it in one controller. Okay, because in the previous table what we have learned, one is good at one thing and the other one is good at the other thing. So all the three response time overshoot error is not available completely in any one controller. So we wanted a better response time, better overshoot suppression, and less error we are looking for. So we wanted to go for a combination here. So combination we have first type, as we have seen here, they are proportional and integral together. We can have it in an additive fashion. So response of proportional integral controller, sorry, proportional controller and response of integral controller, we are going to add and we are going to generate as a controller output. Okay. So by doing this, what advantages we have? Zero steady state error, which is the advantage of integral controller, is retained as it is. It is still there. So you will see that the integral, because of the integral control action, we found that the steady state error is zero. Okay. Whereas stability and peak overshoot was the problem previously when we used integral controller alone. Now in combination with the proportional controller, we found that stability and peak overshoot improves. So stability and the peak overshoot parameter, if we talk about, it has improved with, when we found integral is used in combination with the proportional controller. Disadvantage, as we have seen the transfer function, we have a pole at the origin that always gives a stability low. That stability low still persists. Okay, though there is an improvement, but it is not a perfect stable situation. It is still sensible to instability with a few parameter change in the system. And it is a very slow reaction to disturbance. So reaction to disturbance is very slow because we have proportion and integral together here. So I'll continue the next type in the next class. I would like to stop at this point. Thank you.